Have you ever wondered what's really going on under the hood when you tap your phone screen or click your mouse? Well, today, we're going to peel back the curtain on all those devices we use every single day. We're going to uncover the universal blueprint that, believe it or not, powers pretty much all of modern computing. So let's just start with a quick question. Think about it. You've got your phone, your powerhouse gaming console, and your laptop for work. They look totally different, right? They're built for completely different things. But what if I told you that at their very heart, they're all basically the same?
No, seriously. All the incredible technology we have today, it's all based on one single brilliant design concept. And it was dreamed up by the mathematician John von Neumann way back in the 1940s. It's an idea so powerful, so elegant, that it's still the foundation for almost every computer out there.
All right, so here's our game plan. First, we're going to break down that universal blueprint. Then, we'll follow a single command on its little journey inside the machine. After that, we'll get into the secret of how your computer can do a million things at once. And finally, we'll look at how all these different parts actually talk to each other. Okay, first up, that foundational design. It's called the von Neumann Architecture, and it really all comes down to three simple yet totally game-changing ideas. So here they are, the three pillars. First up, unified memory. Now before this, a computer's instructions, the program, were kept totally separate from the data it was working on. Von Neumann said, hey, why don't we put them both in the same place? It's like putting your recipe book in the same pantry as your ingredients. Genius. Second, addressable locations. Every single byte in that memory has a unique address, like a street address for a house. This means the processor can find any piece of data or any instruction instantly, no searching around. And third, sequential execution. The computer just follows the program step by step, one instruction after another, nice and orderly.
So that's the blueprint, but how does it actually, work? Well, let's follow the life of a single tiny instruction as it makes its way through the computer's brain. This is a journey that happens billions of times every single second.
And to make this super easy to understand, we're going to use this great analogy. Think of your processor, the CPU, as a master chef. The computer's memory? That's the pantry. And it's stocked with all the ingredients, the data, and the recipe book itself, the program instructions. So a single instruction is just one line in that recipe.
Now, everything you do on a computer, and I mean everything, gets broken down into millions of these little commands, and each one goes through this whole life cycle. Now, don't let all the technical terms on this chart throw you off. It really all boils down to 4 main stages. Let's walk through them. Okay, step 1 is instruction fetch. It's simple. Our chef, the processor, walks over to the pantry, the memory, and reads the next step in the recipe. It just fetches the instruction it needs to do next. Next up, instruction decode. So the chef reads the line, add 2 eggs. He has to understand what add means and that he needs 2 eggs to do it. For a computer, those eggs are called operands. The processor is decoding the instruction to figure out exactly what it's supposed to do and what data it needs to do it.
And that brings us to data operation. This is the action step. The chef actually cracks the eggs and starts mixing. Our processor is doing the math, the addition, subtraction, whatever the instruction called for. It's actually doing the work.
And finally, operand store. The chef puts the bowl with the mixed eggs back down on the counter. The processor takes the result of its calculation and writes it back into memory so it can be used for the next step of the recipe. Or it might send it to an output device, like your monitor, so you can see it.
Now here's where it gets really interesting. A command that looks super simple, like add BA, which just means add the number at memory address B to the one at address A, isn't just one quick trip. The processor has to first go fetch the instruction itself. Then it has to go back to memory to get the number from location A. Then it has to go back again to get the number from location B. Then it can finally do the math. And then it has to go back one last time to store the answer. It's this constant, super fast conversation with memory. So we've got our chef, right? Working away, following the recipe, step by step. But what happens if the oven timer goes off? Or the doorbell rings? Well, that's where the secret sauce of modern computing comes in. It's called an interrupt.
An interrupt is, well, it's exactly what it sounds like. It's basically a tap on the shoulder for the processor. It's a signal from your hardware or software that says, hey, stop what you're doing for a tiny fraction of a second. I need you right now. So the processor carefully puts a bookmark in its recipe, handles the urgent request, and then goes right back to where it left off. So why is this so critical? Because compared to a processor, we humans are moving in slow motion. Without interrupts, your computer would be waiting for you to type a letter, and the whole time the processor would just be sitting there, doing nothing, twiddling its digital thumbs. But with interrupts, the processor can be working on thousands of other things in the background. Your keyboard only has to interrupt it for a microsecond when you actually press a key. It's a game changer for efficiency.
And this image just lays it all out perfectly. Look at the top diagram. See all those huge gaps of wasted time? That's the processor just waiting around for something slow, like a hard drive. But now look at the bottom diagram. The processor fires off a command and then immediately gets back to work on something else. It only stops when the device sends an interrupt saying, "Hey, I'm done." This is literally why your music doesn't stutter every time you move your mouse.
Okay, so we've got our processor, our memory, all these devices sending instructions and interrupts all over the place. But how do they physically communicate with each other? What are the roads that connect everything?
Well, for decades, the answer was something called a bus. And the best way to think about it is like a single-lane road that connects every building in a town. It works, but only one car can be on the road at a time. So if your graphics card is talking to memory, your hard drive just has to sit there and wait. It creates a massive traffic jam.
So to fix this bottleneck, modern computers got a huge upgrade. They moved to a system of point-to-point interconnects. So instead of that one shared road, imagine every important building gets its own private multi-lane superhighway directly to the other buildings it needs to talk to. It is so much faster and way more efficient.
And this table here sums it up perfectly. We move from that old shared bus, the single-lane road, to modern tech like Intel's QPI, which are like private express lanes between processors. And then you have PCIe, which acts like a dedicated, high-speed on-ramp directly to the motherboard for really demanding stuff like your graphics card or a super-fast SSD.
So let's just boil it all down. Underneath all the apps and operating systems, your computer is really just running on a few elegant core ideas. There's a 75-year-old blueprint for how it's built. It runs a constant 4-step cycle to get any work done. It uses a clever system of interruptions to multitask. And the connections inside have evolved from slow, single-lane roads into a network of private superhighways. And that really just leaves us with one last, kind of mind-blowing thought. This incredible architecture has served us for 3/4 of a century. It took us from computers the size of a room to supercomputers we carry in our pockets. But as we keep